Welcome to my tutorial on sp3 hybridisation. The aim of this tutorial is to give you a better understanding of what an sp3 hybridised carbon atom is. So we're going to pay particular attention to the types of orbital that an sp3 hybridised carbon atom has and how these orbitals lead to the carbon being tetravalent, i.e. lead to it having 4 bonds to other atoms, and also how the orbitals that these hybridized carbon atoms are arranged in a tetrahedral geometry around the central carbon nucleus, which means that these 4 bonds that carbon has, if it's sp3 hybridized, will also be in a tetrahedral geometry. So that's what we're building up to, and we're going to do it in the same way as we did in the lectures. We're going to build the material up. So if you remember from the first lecture I gave, I said that the length and strength of any bond within a molecule depends on the type of orbitals that are overlapping to give that bond. So if we compare, for instance, hydrogen and methane, in hydrogen you have this bond that results from the overlap of a 1s orbital from each of these hydrogen atoms, and if these s orbitals overlap you get this bond that is 74 picometers in length and 436 kilojoules per mole in strength. Compare that to the bonds in methane. These bonds are between a carbon and a hydrogen, so they'll arise as a result of overlap from the 1s orbital of a hydrogen with a different type of orbital from the carbon. And because you have this overlap of different types of orbital, you get a different bond length and a different bond strength. So there's the first important concept to keep in your mind, that the length and strength and character of any bond depends on the types of orbitals that are overlapping. So we then moved on and thought, well, let's consider the structure of methane, and more specifically let's consider the types of orbitals that this carbon atom has to allow it to have these 4 bonds to hydrogen that are all of exactly the same length and strength. Because if you look at the original electron configuration that I put up for carbon, you'll see that these two don't match up. This carbon is tetravalent, it forms 4 bonds, whereas in this electron configuration for carbon you see that in the valent shell, the second shell, there's only 2 unpaired electrons. So if there's only 2 unpaired electrons, you're only going to get 2 bonds, because only unpaired electrons will take part in covalent bonding. So this electron configuration does not accurately describe the orbitals that are present in this carbon in methane. And it's noteworthy to point out at this point that the carbon in methane here is sp3 hybridized. So if we understand the electronic orbitals in this carbon for methane, then we understand sp3 hybridization. So this is our model compound here. So anyway, so let's move on and think about what could be changed with the electron configuration for carbon to make it tetravalent. And you could maybe think, well, maybe if we excited one of these electrons from the s orbital up into the available p orbital, that would give us 4 unpaired electrons. That surely would account for the tetravalent carbon atoms we see in organic molecules. But if you look at this electron configuration, you'd see that one of the bonds in methane, if this were the correct electron configuration, one of the bonds from methane would result from the overlap of this s orbital with one of the s orbitals of hydrogen, and the remaining 3 bonds would result from the overlap of a p orbital with an s orbital of hydrogen. So what you get is you get bonds of differing length and strength. So again, when we consider that all the bonds in methane are the same, this does not give an adequate description of the orbitals that are present in this carbon atom here. So that brings us nicely on to sp3 hybridization, which, as you no doubt have worked out, is the correct quantum mechanical description of the orbitals that we see in many carbon atoms in organic molecules. And all sp3 hybridization is a combining of the individual wave functions for the s and p orbitals, as originally shown here, to obtain wave functions for a new set of orbitals. And these new orbitals will have in varying proportions the properties of the original orbitals. Okay, so a more simple way of saying that is that the actual correct representation for the electron orbitals in a carbon atom in its valence shell is that you have these 4 orbitals that are all exactly the same and therefore on exactly the same energy level, and these 4 orbitals could be considered as arising from mixing this s orbital with these 3 p orbitals to give these 4 new orbitals, each of which contains 1 part s characteristic and 3 parts p characteristic. So these 4 orbitals are mixing to give these 4 new orbitals, and these orbitals are said to be degenerate, i.e. they're all on the same energy level. Therefore, when you put the 4 valence electrons of carbon into them, you'll put 1 into each empty orbital first to give your 4 unpaired electrons, therefore a tetravalent carbon atom. And because all of these orbitals are the same shape and energy level, all the bonds, if they're bonding to hydrogen, will be exactly the same. So that's it. That's the electron configuration consideration of this. So let's give a diagrammatic representation of this hybridization. So shown here are the 4 hybrid orbitals arranged in a tetrahedral shape around the central carbon atom. Each of these hybrid orbitals looks like this, an asymmetric dumbbell shape. So what we're saying is that the original spherical s orbital and the original 3 dumbbell shaped p orbitals all mixed together to give 4 of these new type of hybrid orbitals which have this asymmetric dumbbell shape, and these are called sp3 hybrid orbitals because they're 1 part s and 3 parts p. And these 4 new orbitals will arrange themselves around the central carbon atom in this tetrahedral geometry. So shown here is a video depicting this hybridization. So what we'll see first is the 4 original orbitals coming into picture, and then we'll see them mixing to give these 4 new orbitals, which are hybrid correct orbital representations. So here's the 2s orbital, spherical, and in yellow the 3 2p orbitals that we originally put up in our electron configuration. So they will come in, and then we'll see them all mixing up to give our 4 new hybrid orbitals, which are the correct representations for the valence orbitals of a carbon atom. And then we'll do a 3-dimensional trip around this carbon atom to show the 3-dimensional arrangement of these hybrid orbitals, and this is the tetrahedral 3-dimensional shape that I've talked about. So just to highlight one of these orbitals, this is a hybrid orbital. You've got your large lobe here, and then sticking out the back you've got your small lobe, and you've got 4 of these, and as I said, they're arranged in a tetrahedral geometry. That's because each of these orbitals contains 1 electron, and an electron carries a negative charge, and like charges will repel each other, so each of these orbitals are repelling each other. So they adopt this tetrahedral 3-dimensional shape because this is the orientation that allows them all to be as far apart from each other as is humanly possible. So that's as far as we need go with describing hybridization. Just to quickly finish off, just a quick description of the tetrahedral shape again. So these is some of the representations you may see for the shape of an sp3 hybridized carbon. The central ball here in this model is the carbon. These are the 3 hydrogens. This is probably the best representation. So you imagine that in the center of this pyramid there's the carbon atom. Each of these balls is a hydrogen. So if you draw a line out from the center to these spheres, they're the 4 bonds that the carbon has in methane. But if you draw a line in between each of these spheres, what you'll end up drawing is a trigonal based pyramid, and that describes this tetrahedral shape of a carbon atom and its 4 bonds. And as stated here, each of these bonds will have an angle between them of 109.6 degrees. So that's it. I hope it helps.